Welcome back to this video on proof. Now we're looking at proof by mathematical induction, which I'll introduce to you in this video, and then subsequent videos will be using a mathematical induction to prove divisibility results, general term of a recurrence relation, and statements involving matrices. Now, proof of mathematical induction, or by mathematical induction I should say, usually involves 4 steps. So step 1 is the basis step. And for this step we need to prove that the general statement is true for n equals 1. Next comes the assumption step, where we assume that the general statement is true for n equals k. Step 3 is the inductive step. This is where we show the general statement is true for n equals k plus 1. And then finally the conclusion step. This is where the general statement is then true for all positive integers of n. Now this essentially works because if n is true for 1, okay, then you're assuming n is true for k when k equals 1. And when you're showing that n is true for k plus 1, well, if it's true for 1, therefore you've shown it's true for n equals 2. And if it's true for n equals 2, you've shown it's true for n equals 3, and so on. Okay, so that's how it's then true for all positive integers of n. Now, the actual kind of process through doing this is following these 4 steps, and it's kind of straightforward. You just need to practice quite a few, and then you'll be like second nature with these. So let's have a look at an example. Okay, so proof by mathematical induction that for any positive integer n, the sum of r between 1 and n is a half n plus 1. So this formula we learned in the last chapter, the last few videos ago, and now we're going to use mathematical induction to prove it. So first we're looking at step 1 when n equals 1, and we're going to substitute that in. So our left hand side is the sum from when r equals 1 to 1, because n is 1, of r squared. Of r. And that is just going to be equal to 1. Then the right hand side is a half times 1 times 1 plus 1. So that's a half times 1 times 2, which is also 1. So now as left hand side equals right hand side, the summation, sorry for my pausing when I'm trying to spell, I find it hard to write and spell the words when I'm saying them. Okay, so the summation formula is true for n equals 1. So that is our first step done. Now the second step, the assumption step, is now that we assume it's true for n equals k. So assume that the summation formula is true for n equals k. And then we write it out with k. So that means it's the sum from r equals 1 to k of r, and this should equal a half k, brackets k plus 1. Okay, so now I've done my n equals 1, shown it's true, my assumption, which is step 2, assume true for n equals k, and then just substitute k into the summation formula, which we're assuming is true. Now we need to do the induction part. So this is when we are looking at n equals k plus 1. So n equals k plus 1 now. So this is what we've got. Our summation formula, r equals 1 to k plus 1 of r. Now, if I'm summing, so let me just come down here a second. So if I was summing this to 51, I could say that this is the same as the sum to 50 plus, and then substituting the 51 into that r. Yeah, or if it was, you know, a little bit more complicated, so say this was an r plus 2 squared, then this would be, you know, I could split this up into the sum to 50 plus 51 plus 2 squared, which is the 52nd term. You know, I could, for example, call that sum to 49 plus the 50th term plus the 51st term, because each term is just substituted in to this. Yeah. Now that kind of process I'm going to apply up here. So this between r equals 1 and k plus 1 is going to be the same as the sum of from 1 to r plus, and now I'm substituting k plus 1 into this. Okay, now this sum of r between 1 and k is here, so we can swap it for this one. So our next line will be a half k plus 1 plus k plus 1. Now it's just a matter of some manipulation, and we need to get it into this kind of form, but with k plus 1 instead of n. So basically we want a half k plus 1, k plus 2. Okay, and at the moment, you know, I can't see that, but let's factorize out the k plus 1, and that leaves me a half k plus 1. Okay, and then if I take that half outside, that gives me a half plus k plus 2, because the half times k is a half k, and the half times 2 is the 1. And then just to make it obvious, I separate it out into the k plus 1 in terms of n. So we got half k plus 1, k plus 1 plus 1. Okay, so therefore that's now me using the induction to show that it's true. Okay, so therefore the summation formula is true for n equals k plus 1. Okay, So now we're on to our final step, the conclusion. Okay, so it's basically talking about the result is true for n equals 1, and steps 2 and 3 imply that the result is true for n equals 2, and they continue to imply that it's therefore true for n equals 3, n equals 4, n equals 5, and so on. Okay, so that's what you want to say. Now, you know I've struggled sometimes to write, spell, and speak at the same time, so I'll just write this next bit without speaking. Okay, so that is my conclusion. So if the summation formula is true for n equals k, then it's been shown true for n equals k plus 1. As the result is true for n equals 1, it is therefore true for all positive n by mathematical induction. Okay, so you're basically saying that you've shown it's true for n equals 1. Then you basically rewriting that, assuming it's going to be true for all of k, where n is any value. But when k equals 1, you then shown it's true for k for n equals 2, because you've shown it true for k plus 1. If that makes sense. So it kind of snowballs then from there. If it's true for 2, it's true for 3, it's true for 3, it's true for 4, and so on. I totally understand that this is kind of a new concept, and you know, for some of you, you'll find this, you know, a little confusing, maybe, but just practice it, understand the steps, okay, learn roughly how to write the conclusion, because it's pretty much the same for all questions, and hopefully, you know, once you get the hang of doing this all completely, then you'll start to understand it. So don't expect everyone to totally get this straight away. I didn't when I first did it. You know, I had to learn to do it first, and it's only through that process by the end then, you know, it suddenly clicked one day. It makes total sense now. But initially, you know, I didn't worry. I knew that, you know, eventually through the process of learning it, it would start to make sense. Okay, so we're going to have a go. I'm going to set you a couple of questions. I'm going to set you the r squared and the r cubed ones from what we've done in the last unit, and then I'll set you another kind of one that's shown up in a past paper, and then we'll go from there. And just before we do, don't forget to like the video if you're finding it useful so far, If you haven't subscribed yet and you are taking A-level maths, then definitely subscribe. Obviously it helps me out, the more people that subscribe, and for you it just helps you find the channel again and support us. And if you want to support me further financially, you can hit that join button, join for a month or longer, totally up to you. Okay, there's not too much on the members page right now. There's just a few videos, but you'll also notice there are a few videos dedicated to particular members. If you sign up as a big fan, then you can ask for help, and I will make the odd video to help you out personally. Okay, so that's that. Anyway, let's get back into this video. So these are the three questions, the r squared and the r cubed from the last set of work, and then just one other past paper question here. Okay, so pause the video anytime now, and then we'll go through the answers afterwards. Okay, so first step, n equals 1. So left hand side is the sum of 1 to 1 of 1 squared, which is just 1. The right hand side is 161 times 2 times 3, which is 1. Left hand side equals right hand side, and then of course assume true for n equals k. So n equals k plus 1 now. Squared, isn't it? And then substitute the k plus 1 into the term l squared. Oh, sorry, I missed a bit down here. This would be between 1 and k. My apologies, missing that bit out, because that's what I need to substitute in up here. So 1/6 k plus 1, 2k plus 1 plus k plus 1 squared. Now k plus 1 appears in both of these, so let's take that out, and we're going to take the 6th out. Okay, so in here, in the first bit now, is going to be a k, 2k plus 1, plus 6 times k plus 1. Okay, so if I take k plus 1 and the 6 out, I get k, 2k plus 1. And if I take k plus 1 and 1/6 out, I've got to multiply by 6 the remaining k plus 1 there. So I get 1/6 k plus 1. Now inside I need to expand, simplify and factorize basically. So 2k squared plus k plus 6k plus 1 2k squared plus 7k plus 1. Now I'm going to factorize this, and it's k plus 2 and 2k plus 3. Okay, so 2k squared, 3 plus 4k is 7k, 2 times 3, that's 6, what am I doing? 6. That's 6. Apologies. And then what I like to do is write it out as the k plus 1 so that you can clearly see the k plus 1 replacing the n's. Okay, so therefore the summation formula is true when n equals k plus 1 and so on. And there, just squeezing on the bottom, is the conclusion step, etc. Okay, that's going to stay the same for all of the ones that we're doing today. Right, let's have a look at question 2. So r cubed, now start with n equals 1, left hand side, so that equals 1. I'll put the right hand side here this time. That equals 1. Okay, so as left hand side equals right hand side is true for n equals 1, assume true for n equals k, therefore between r equals 1 and k, r cubed equals 1/4 k squared k plus 1 squared. Now n equals k plus 1. So we are looking at between r equals 1 and k plus 1 of r cubed. Okay, now we can replace the sum to k with 1/4 k squared k plus 1 squared k plus 1 cubed. Now we take out the k plus 1 squared and we'll also take out the 1/4. So that leaves me with k squared from this one because I've taken that and that out, plus 4 k plus 1. So it's 1/4 k plus 1 squared, and then I've got k squared plus 4k plus 4. Now this is going to be k plus 2 squared. K squared, 2k and 2k is 4k, and 2 times 2 is 4. Yeah. And then just to write it the way I like, and then it follows this pattern: n squared, n plus 1 all squared, k plus 1 squared, k plus 1 plus 1 squared, and then multiplied by the 1/4. Okay, so that's the third step, the mathematical induction. All that's to follow is that therefore the summation is true for n equals k plus 1, and then my conclusion. And here we have now that final step there. Now let's have a look at question 3. So same start as always, n equals 1. So let's look at the left hand side first. This is r, 1 minus 1. So that's going to be 0. Right hand side, a third times 1 times 2 times 0. So that's 0. So left hand side equals right hand side. So therefore we're going to assume true for n equals k. This is 1/3 k, k plus 1, k minus 1. Now we do the induction step, so n equals k plus 1. So this is r minus 1 between 1 and k plus 1. And it's between 1 and k plus, and then we're substituting k plus 1 in, k plus 1, k plus 1 minus 1. And then I substitute in, so this is 1/3 k, k plus 1, k minus 1, plus k, k plus 1, isn't it? Because this is k plus 1 and this is going to be just k. Now I can factorize out 1/3 k, k plus 1. And that leaves me with k minus 1 from the left plus 3 lots of k. No, just 3. Isn't it? Because I've taken a k and k plus 1 out. So that is 1/3 k, k plus 1. And this is now k plus 2. Okay, now as it stands, it doesn't necessarily look exactly like this. But let's look at putting in the k plus 1s. So this is 1/3. Now instead of k, we've got k plus 1 minus 1. And then we've got k plus 1. And then we've got k plus 1 plus 1. Okay, so it gives me the 3 terms. If I rewrite them out, so k plus 1 first, k plus 1 plus 1, and k plus 1 minus 1. And now that's in the form of this. Okay, so from here now it's just the summation is true for n equals k plus 1 and my conclusion. And there we have it. So if you found this video useful, don't forget to like, comment down below. The next few videos is just going to be based on this, but when it's applied to divisibility, to matrices, and to the general term of a recurrence relation. Okay, so stay tuned for the final few videos in this series.